So, it looks that we have to look back at this picture that I have shown you previously, and it seems that some of the possibilities suggested in 2009, at least in the area of diabetes, seem to be closed. It's rather unlikely. We may be surprised, of course, by some unsuspected finding in the future, but that will be extremely rare, I would say, that a new polymorphism will be found with very high odds ratio of effect on diabetes. So the research is moving more toward the left-hand side of this picture, towards rare allele, some of them with large effect, and also low-frequency variants. By low frequency, we mean something which is in the area of 1%, 0.5% minor allele frequency in the general population. I would like to raise now the issue of so-called missing heritability. Discussing this issue in detail is clearly beyond the scope of this lecture, but I would like to show you the data which are in the red box over here. And basically you have 10 complex diseases, various complex diseases, some of them cancers, some of them central nervous system diseases, metabolic diseases like diabetes, coronary artery disease. And the point I want to make is, first, the heritability of these diseases is quite high. It's always and consistently in the range between 0.4 and 0.8. So it means that roughly 40 to 80% of variability, inter-individual variability in the population, we see should be explainable, should be explained by genetic factors. So quite a large proportion. And on the right-hand side, I would like to show you the proportion of heritability that has been explained so far by genome-wide association study. And it's really small, like central nervous system diseases like schizophrenia, bipolar disease are notoriously on the low end. Very little has been explained so far, and people claim that this is probably because of a larger heterogeneity of these diseases than the other diseases studied here. But even in the best case examples, it looks like 30% of heritability has been explained so far. And this is a mystery that has been dubbed a missing heritability. By missing heritability, people have been making associations with dark matter in astronomy. So astronomers say that they can see dark matter, they can see the effects of dark matter, but they don't know where in the universe it's located. Here the situation is similar. We know that these traits are heritable, but we cannot pinpoint the polymorphisms that are responsible for these diseases. So as I said, it's beyond the scope of this lecture to discuss this in detail, but I would like to share with you some thoughts on what missing heritability may mean to the future of genotyping, the future of genetic studies. So, first of all, we have to ask the question why this is important, why we care about missing heritability. And the answer is very obvious. There may be hidden treasures out there. There may be hidden pathways for prediction of a disease. There may be hidden pathways for treatment of a disease that we do not exploit currently because we don't know that this given pathway is associated with, say, diabetes in any way. What are the potential explanations of this missingness of heritability? So one obvious possibility is to look at the left-hand side of the picture. So look at rare alleles with the frequency below 1%, even below 0.1% in the population, but with large effects. So almost saying that diabetes would be a Mendelian disease, however, with large number of polymorphisms, private polymorphisms, each of them having having a large effect. I'm not saying that this is the case, but just this is a possibility. And then there is this daunting possibility that there are hundreds of rare variants of small effects that it's really not practical to talk about because they have too small effect. Okay, so at this point we have to turn to the second revolution, that technological breakthrough that happened in the area of genetics in the past few years. At the beginning, in the 2007, and then in 2009, these systems became commercially available. The systems which were called next-generation sequencing. Next-generation sequencing because they used a completely different strategy of sequencing compared to the old Sanger method. Sanger method which dominated the field of sequencing for 20 plus years. The term next-generation sequencing was coined simply because these systems were orders of magnitude more efficient than the old sequencing machines, Sanger sequencing machines. It's hard to believe, but it's true that if you buy today a machine for next generation sequencing, you will have in your lab the sequencing capacity that is higher than the sequencing capacity in the whole world just 5 years ago. So right now in your lab you can sequence more than what the whole world was sequencing just 5 years ago, and these techniques were not available. What is the throughput? The highest attainable throughput with the current technology is roughly 600 gigabases per run. And the run lasts about 2 weeks. So if you imagine that the human genome is about 3 gigabases, 3 billions of base pairs. So you can, in a single run, in 2 weeks, you can sequence 6 human samples at 30x coverage. We need to do it with high coverage, not just with 1x coverage, because this is random sequencing. So when you achieve 30x coverage of the whole genome on average, you will obviously have areas which just by chance have been sequenced 50 times, 60 times, and some areas which have been sequenced maybe just 10 times or less. And in order to be able to tell this is a heterozygote or this is a mutant homozygote, you cannot just tell that if you have 1x or 2x sequencing coverage. You would have to have at least 20, 30x coverage and see a heterozygote in about a half of these reads. So if you do it 30x, the current state of the art is to accept a polymorphism if you see it in at least 10 reads. So not less than 10 reads in order to say here is a polymorphism. The cost of genotyping, of sequencing, dropped down quite dramatically. We have to remember that the Human Genome Project, which completed just 10 years ago and was done entirely with Sanger sequencing, costed about $100 million. $100 million. And now you can sequence the whole genome of a given person with less than 10,000. So if you invest in stocks exchange, they tell you that old performance is not a promise of the future performance. So we cannot say for sure that price will be dropping down constantly. But it looks like the $1,000 genome is attainable within the next few years. And $1,000 genome means that the cost of sequencing the whole genome will be comparable to doing an NMR scan or CT scan in countries like United States. I think in Poland it would be still more expensive to sequence than to do a CT scan. But in the United States it's probably comparable. So for today it's still too expensive for routine use to use next generation sequencing of whole genomes. However, it's worth remembering that this technology allows multiplexing of samples in some cases 40-fold, in some cases even up to 100-fold, in which in the process of synthesis you add unique barcodes to sequence DNA. So you know from which person this DNA comes from. And instead of doing whole genome sequencing, you can do exome sequencing, so sequence all exons present in the human genome, or you can do targeted sequencing of regions that have been previously pinpointed by genome-wide association studies. I would like briefly to show the early applications of this method. So this is the study published in 2009 with rare protective polymorphisms in type 1 diabetes. I just would like to ask you to look at the red boxes. I'm not sure if this is clearly visible, but the point is that the frequency of these polymorphisms in cases with type 1 diabetes is clearly below 1%. In controls is 2.5%. So it's really almost impossible to detect this with the current microarray technologies. Most of the microarrays currently used, they have a content of about 1 million polymorphisms, which is a lot, but basically allows you to detect associations with polymorphisms of a frequency higher than 5%. The newly released microarrays can go up to 4 million polymorphisms on one array, and the producers claim that you can go down to 1% of to association studies with polymorphisms of minor allele frequency of 1%. So these are just at the edge of detection. Another, maybe even more impressive example, outside from the area of diabetes though, was published just 2 months ago, and this is the study in sick sinus syndrome. So basically people who have bradycardia, which may be dangerous, and the sick sinus syndrome is a major indication for pacemaker implantation in these people. This is a study in Icelandic group with an allele frequency of just 0.4% in Icelandic population. However, if you look at this mutation, the odds ratio is 12.5. So it very well fits into the scenario of rare polymorphisms with very high effect. It has been calculated that if you do not have this mutation, your lifetime risk of developing sick sinus syndrome is 6%. But if you do have it, your chances of getting sick sinus syndrome is 50%. So this polymorphism has a very high predictive value for the people who have this polymorphism, not for the general population, obviously. And I would like to share with you